Hey man, do you ever feel like learning about bone healing just seems like an association of a bunch of terms? For example, if you have an articular fracture, you want to heal with primary bone healing. In order to do so, you're trying to get absolute stability through compression in order to minimize the motion of the fracture site so that strain is minimized and there will be no callus formation. And in order to do all this, you probably need to do a direct reduction.
Yeah, and for diaphyseal fractures, you try to get secondary bone healing. And for that, you can try to achieve relative stability through a bridging construct that allows for some motion at the fracture site, resulting in higher strain and callus formation as the bone heals. And in order to do that, you can use indirect reduction techniques.
I guess the benefit of a system like this is that it makes it easier to learn, but I feel like there are some things that the system doesn't really explain. Like it doesn't really explain the phenomenon of plates breaking if the bone doesn't heal.
Or how different screw spreads affect the stress experienced by the plate and the longevity of the fixation.
And it doesn't really discuss how the biology of different patients affects bone healing, even though we know that patients at different ages and levels of health heal at different rates. And what's the deal with strain? I feel like we've all memorized the formula where you have L as a fracture gap and delta L as a change in the fracture gap, and strain is defined as delta L over L.
Well, for primary bone healing, you need very low strain, whereas for secondary bone healing, you can have slightly higher strain.
But it's inherently confusing since both the numerator and the denominator can change. If you make the construct a bit stiffer and the amount of motion decreases, the strain actually goes down. But paradoxically, another way to change the strain is to make the fracture gap wider. According to the definition, this also decreases strain.
And by that definition, if we continuously make the gap larger and larger, strain continues to get smaller and smaller.
Yeah, in general, it can be pretty confusing trying to apply the concept. And that's why we developed the fracture fixation model. It's not really trying to convince you of anything new, but we think it helps to combine and repackage a lot of the things we already know about fracture fixation into a single coherent model.
And this is what it looks like. At first glance, it might look like a lot, but we promise it is built from smaller building blocks which all come together nicely to explain the complex phenomenon of fracture healing after fixation.
One key thing to note is that everything in this model is based off the concept of stiffness levels, essentially how much motion is allowed in the fracture environment. The types of tissue that form and what happens to the fixation construct are all based off this concept.
At its very core, this model consists of just two main pieces, a biology piece and a mechanics piece.
Let's look at the biology portion first. For this model, we assume that the biology of fracture healing can be simplified into four general processes: fibrous tissue formation, callus formation, and bone resorption. All of these processes are occurring simultaneously, but at different rates. The rate at which these processes occur depends on the environment. In particular, it depends on how much motion is occurring at the fracture site. If there's a lot of mobility at the fracture site and the environment is not very stiff, the tissue that is preferentially formed is fibrous tissue. But notice that the tissue forms fastest at a specific level of stiffness. However, at stiffness levels outside of the optimal range, such as when the environment is too stiff or not stiff enough, the formation rate of the fibrous tissue drops off. This is also true for the other tissue types. At higher levels of environmental stiffness, callus is preferentially formed. And at the highest levels of stiffness, bone is preferentially formed. At low levels of stiffness, when there's a lot of motion, bone actually gets resorbed. This can be seen clinically when the screws are toggling and a snow angel shadow appears around the screw. Each type of tissue has its own properties, with fibrous tissue having the greatest potential formation rate and bone having the least. Additionally, as each tissue type forms over time, they contribute different amounts of stiffness to the environment, with each unit of fibrous tissue contributing less stiffness than each unit of bone. Now, when we talk about fracture healing, we are really mainly interested in the portion at the far right of this graph, so we will just zoom in on this section and rescale the x-axis. And to help simplify the model, we will ignore the fibrous tissue formation since it contributes relatively little to the stiffness. And finally, we will stand it up so that stiffness is on the y-axis and make it point to the right to make the final product for the biology side. And that's it for the biology section of the model.
But before we move on, let's just backtrack a little. We want to keep in mind that the numbers presented in this model are all relative and should serve to mainly demonstrate directionality. For example, the callus formation rate is not a fixed value, but varies from patient to patient. Biological activity changes with age, with children tending to form callus much more robustly than a normal adult or someone with impaired metabolic activity. This can be demonstrated by the different shapes and magnitude of the curves. Similarly, the addition of various drugs can affect the shape and height of these curves. For example, the use of bisphosphonates would be expected to reduce the rate of bone resorption and dampen the shape of the curve.
Now let's start to take a look at the mechanics section of the model. Notice there are three lines on the mechanics side of the model: bony stiffness, fixation stiffness, and overall stiffness. Overall stiffness is the stiffness of the overall environment and is just the bony stiffness and the fixation stiffness added together.
Bony stiffness is the amount of stiffness that the bone contributes to the overall environment. Imagine a fracture that has nice cortical keys that can be pieced back together and compressed. If the fracture ends are compressed together, there will be a lot of bony stiffness. Now, imagine a fracture with a lot of comminution. The fracture ends can't be compressed together to make a stable construct, so the bone will contribute very little bony stiffness. Finally, imagine a fracture that could have been compressed but was unfortunately fixed in a way that there was a gap. While these fracture fragments could have been put together in a way that would contribute to a lot of bony stiffness, due to the gap, it does not contribute any bony stiffness at all.
Now let's consider fixation stiffness. This is the stiffness that we are most able to control in the operating room based on the implants we use and where we place our screws. Here are some of the few ways the fixation stiffness can be increased. Using a thicker plate increases the fixation stiffness. Using a thicker nail increases the fixation stiffness. And putting the inner screws closer to the fracture gap will also increase the fixation stiffness.
Now let's go back and take another look at the mechanics graph. Notice that the x-axis of the graph is time. Time 0 is the state of the fracture at the initial point of fixation. Time 1000 is an arbitrary time in the future, but for our purposes, let's say that it is the time at which we decide whether the fracture has gone on to union or non-union. In this case, at time 0, there is 0 bony stiffness and a moderate amount of fixation stiffness. The overall stiffness of the overall construct is the same as the fixation stiffness, since the bone is contributing nothing to the overall stiffness at this point in time. Over time, the bone and fixation individually change in stiffness, resulting in changes in overall stiffness. Let's look at these lines individually.
If we focus on just the bony stiffness line, we see that the stiffness is increasing. When the bony stiffness reaches maximum stiffness, the bone is fully healed. If you look closely, the line actually changes in slope as it progresses in time. This is because the different types of tissues are forming at different rates and contributing different levels of stiffness. Additionally, bone resorption is also occurring. We will discuss how the biology is incorporated a little later.
Let's look at the fixation stiffness line. The maximum fixation stiffness occurs at time 0. Once the fixation is placed, it starts to decay, and the stiffness starts to drop. However, once the bone fully heals, the fixation stops decaying.
So what affects the decay rate of the fixation? There are really two contributing factors to the decay rate, which is the stiffness of the overall environment and the stress concentration within the fixation. We already talked a little bit about overall stiffness, which is the bony stiffness plus the fixation stiffness at a particular point in time. So let's focus on stress concentration.
This is actually a concept that is probably already pretty familiar. Let's say you have a pencil that you're trying to break in half. If you place your fingers and thumbs at the far ends of the pencil, it may bend, but it will be difficult to break. However, if you put your thumbs close together, it becomes much easier to break the pencil in half. This is because the stress is concentrated between your thumbs, and when you move your thumbs close together, the stress gets concentrated over a smaller area of the pencil. So here are the two scenarios side by side for comparison. The same thing happens for screws in a plate. When screws are placed closer to the fracture, it concentrates the stress to a smaller area of the plate.
So now we have the two pieces that affect decay rate, overall stiffness and stress concentration. If the overall stiffness is low and there's a lot of motion at the fracture site, the fixation will experience a high decay rate. If the fixation construct is assembled in such a way that increases the stress concentration in the implant, the fixation will also have an increased decay rate. Here is a mechanics graph of a different situation. If we focus on the fixation stiffness line, we can see that the fixation stiffness starts high, but falls dramatically, and eventually hits zero stiffness, which means that the fixation broke and failed.
Let's go back to our original graph one more time and finally look at the overall stiffness line. The overall stiffness line is just the fixation stiffness and the bony stiffness added together. In this case, there is no bony stiffness at time 0, so the overall stiffness is equal to the fixation stiffness. As we move forward in time, the overall stiffness increases since the bony stiffness is increasing even though the fixation stiffness is decreasing. And eventually, the overall stiffness maxes out.
Now that we have both the building blocks, let's look at how the two sides interact together. The biology side can give us clues as to what is happening to the bone since the biology side directs how bony stiffness changes during the bony healing process. If we focus on the early time frame, we see that the overall stiffness is in a range where callus is being primarily formed. This results in a rapid increase in bony stiffness. So by just looking at where the overall stiffness is at any point in time, we can know what type of tissue is being formed at the fracture site at that point in time. In the early stages after this fracture was fixed, there is early callus formation. After the early callus formation phase, bone formation primarily takes over, and the callus is replaced with bone. And for the rest of the time that the bone continues to heal until maximum stiffness, the bone formation continues since the combined stiffness of the bone and the fixation construct provides an environment where the bone is being preferentially formed. Finally, bone healing is complete, fixation decay stops, and everything reaches a steady state.
Now that we know how the model works, let's start to apply the model to some clinical situations to see how it works.
The first scenario is meant to demonstrate primary bone healing. In this scenario, we have a simple fracture that is treated with compression with a lag screw and a neutralization plate. In this case, there is high initial bony stiffness and a moderate initial fixation stiffness with a moderate stress concentration. This is what the graph would look like. Here is the high initial bony stiffness, and here is the moderate initial fixation stiffness. Combining the two results in a very high overall stiffness. As the fracture heals, the bony stiffness increases to maximum stiffness, and this bony stiffness is maintained at the final time point, demonstrating a healed fracture.
In the second scenario, again we have a simple fracture pattern, but this time it is treated with the same fixation, but with a failure to compress the bony fragments together. This results in a very low initial bony stiffness due to the fracture gap, and moderate initial fixation stiffness similar to the previous scenario. But there will be a relatively high stress concentration for the implants since all the movement at the fracture site will be transmitted to the fixation. Here we see the graph with moderate initial fixation stiffness which rapidly decays and breaks. The bone does not have much time to heal, and as a result it is unable to heal and ends up as a non-union.
Next, there is a accommodated fracture treated with a bridging fixation construct. There is very low bony stiffness, moderate initial fixation stiffness, and low stress concentration since the fixation is long and well spread. In this graph, the bone starts with minimal stiffness but eventually fully heals, whereas the fixation starts at moderate stiffness and decays until the bone heals.
For scenario 4, the treatment again is a bridging construct for accommodated fracture. But this time the fixation is less stiff and has an even lower stress concentration. In this case though, the fixation begins at low stiffness and proceeds to fail. At the end of the time frame, the overall stiffness ends up being in a range where callus is preferentially formed, resulting in a hypertrophic non-union.
The treatment again is a bridging construct, but this time the fixation is very stiff with a very high decay rate since the stress is concentrated on a short segment of the plate. As can be seen from the graph, even though the fixation starts with high stiffness, it fails quickly and the bone is never really able to heal. This results in an oligotrophic non-union since the overall stiffness is still below the optimal range for callus formation. In this next scenario, we will demonstrate what happens in an atrophic non-union. We will go back to the same conditions as scenario 3 with an appropriately constructed bridging construct. However, in this case, this patient has reduced biological potential and the formation rate of the bone and callus are therefore reduced. As can be seen, the construct starts at the same starting points, but the construct fails and the overall stiffness ends up in a range where little callus is formed.
For this scenario, the treatment again is a bridging construct, but this time the fixation is very stiff with very low stress concentration since the stress is shared between the primary and supplemental fixation. As can be seen here, the bone starts with minimal stiffness but increases steadily until full healing occurs, whereas there is minimal decay of the fixation.
This model can also be applied to some more complex scenarios. For example, it has been described that in some non-union cases, percutaneous strain reduction screws can be placed across the non-union site in lag or compression mode, and this is enough to help these fractures go on to fully heal. For this scenario, we will start with very little bony stiffness and will be treated with a construct similar to scenario 4, which had a construct with relatively low stiffness and stress concentration, but went on to hypertrophic non-union. However, during the course of fracture healing, additional screws will be placed, which will help slightly increase the fixation stiffness. In the graph for this, the fixation begins to approach failure, and the fate of the bone will likely be a non-union similar to scenario 4. But the placement of additional screws increases the overall stiffness enough that the fracture goes on to heal.
Another relatively complex phenomenon that can be addressed by this model is that of reverse atomization, where micromotion is initially allowed through the use of more flexible construct early in the healing period, followed by a transition to more rigid fixation later on. This transition has been reported to result in a shorter time to union than using either the flexible construct or the rigid construct alone. With the static fixation, there is high fixation stiffness and the bone readily progresses to heal at a certain point in time. With dynamic fixation, there is lower fixation stiffness and the bone also heals but in an even shorter time frame. With reverse atomization, the graph starts at a lower fixation stiffness Then it gets bumped up during the early healing process, resulting in the shortest time of bone healing. This is because the tissue formation is supported by the optimal stiffness environment at the time they're ready to form.
While some of the language introduced in this model may be new, these concepts still relate to traditional terms. Strain is a property that defines the type of bone healing that occurs at the fracture site and is modulated by surgeons through modifying overall stiffness.
Absolute stability is achieved at high rates of overall stiffness, which is a combination of both bony stiffness and fixation stiffness. High overall stiffness results in primary bone healing and no callus formation.
Relative stability occurs at lower levels of overall stiffness, particularly in cases where only low levels of bony stiffness are able to be achieved, and most of the stiffness must be afforded by the fixation construct. This results in secondary bone healing with a period of callus formation, followed by bone formation if the overall stiffness becomes great enough for bone to form.
A hypertrophic nonunion occurs when the resulting overall stiffness at the time of evaluation is in the range of stiffness optimized for callus formation but not for bone formation. Whereas an oligotrophic nonunion occurs when the resulting overall stiffness at the time of final evaluation is outside of the range of stiffness optimized for callus or bone formation.
In summary, this is only a theoretical framework, and of course there are limitations to its applicability, and there are many variations that can occur based on individual patient and fracture characteristics. However, we find it useful to approach fracture problems with these questions in mind. First, what type of healing do I want to achieve? Do I want to optimize my overall stiffness for callus or bone formation?
Next, how much of the overall stiffness can be supplied by the bony stiffness?
How much of the residual overall stiffness needs to come from the fixation construct?
And finally, how do I manipulate the bone and create a fixation construct that will allow the bone to heal before the construct fully decays?
That's it. We hope you find this conceptual framework useful. Thank you for watching.